All right, so in this video lesson, we are going to study about the Green's theorem for line integrals right here. But then before we start right here, as a couple of preliminaries for this topic right here, Green's theorem is only applied, or Green's theorem only applies to those line integrals in two-dimensional spaces. So the vector fields, and it's line integrals for vector field, but we only apply Green's theorem to those vector fields that are in the form of a P, comma Q, right, in those vector fields in R2. Okay, so that's what's specialized about Green's theorem for here. All right. All right. And so before we get into the actual idea about the Green's theorem right here, allow me to introduce the following problem. And as I finish writing down the problem, I will give some more insight details about this kinds of problem right here. All right, so this is what the problem is right here. And you can spend some time writing it down. Okay, but then to give some insight detail about this kind of problem right here, it's a line integral, right? At first sight, it's just simply a line integral as anyone can see it. Okay, it's a line integral, and our curve here, our path here is the curve that's parameterized by this vector value function. So, and as I have mentioned earlier, this line integral problem is a problem where our vector field is a two-dimensional vector field right there. So we have a vector field here being the 2x, comma 2y, okay, and our path here is that parametric system cosine of t and sine of t. And then the variable t is changing value anywhere from 0 to 2 pi. And that's what's making it special about this problem right here. So let's dive in a little further right here. Okay, and so when we're investigating a little further into the parameterization of this curve right here, for this curve C right here, where it's given as the parametric or the vector value function given by cosine of t and comma sine of t, for t is changing from 0 to 2 pi, then for anyone learning in this video lesson, then when you're looking at this parametric curve right here, this, the 2D space curve, you will realize immediately that when you are making a quick sketch of this parametric curve, and it's not that hard at all to sketch that, and so in your experience up to this point in your learning, then this parametric curve is a complete circle. So when t equals 0, we have a start right here, and then it goes around in a positive direction, and then when t equals 2 pi, we end right here. So our path here, our starting point of the path, we go around the curve, we go around the curve, and then the parameterization gives the orientation of this curve, and that's why I know the arrow is pointing that way. And then as we go along the curve, we end up right at that same starting point when t equals 2 pi. Okay, so for t changing from 0 to 2 pi, we produce this curve. And so now physically as a curve itself, what we are facing here is now referred to as a closed curve. Okay, as a closed curve. And furthermore, now closed curve itself, now things are starting to get a little dangerous here, but at least in the world of 2D planes on the x and y plane right here, a closed curve by itself can also be a curve like this, like an H shape right there. Okay, we start out right here and we cross around and come back to the same point, but there's a crossing nature over here, so this is also a closed curve. But you can see that right from your eyes right here, that this closed curve is different from that closed curve I drew in red right here. And so for that matter, the kind of problem we're about to get in here focus on the kind of closed curve that we call simple closed curve, where it's just one loop and then no crossing or anything like that. Okay, and that's what simple closed curve means. And so we're gonna erase this because we won't look into that kind of closed curve. But again, see, and so the path that we're doing, it's at the very zeroth ground right here, then this is a line integral problem, okay, for a path on the x and y plane. But then now when we're looking further into the path turns out to be a simple closed curve where starting point and ending point meets at the same spot, okay, physically on the x and y plane like that, okay, and that's that's opens up a new kind of problem right here. And so now coming back to this problem here as a generality, then this problem really arose right at the moment that we finished studying about line integral. But then maybe in my video lecture that you have learned when I specifically taught about a line integral, I didn't bring up a problem like this in the video lecture, but now I gotta make you realize that in this video lecture here, now I gotta make you realize that this problem really arose at the same time where we finished studying about line integral, okay? Because see, being a path, right? The earlier problem in the video lectures that I finished just to study and investigate about line integrals, and we only study about those paths where it got a clear starting point and a clear ending point. So starting point and ending points were just two different points. But now we're studying those the path where it's a simple closed curve. And so from that matter, from now on, a lot of times, see, because the nature of the path here is being a closed curve, starting point being the same points with the closed curve, and so this integral symbol, this notation right here, comes included with a little circle going around like that. All right, that's to indicate that, hey, it's a line integral in its most usual sense. But on top of that, be aware that this is a line integral where the path is a simple closed curve. That's the kind of problem that we're being introduced in right here. Okay, and so it's one big problem out there that challenged a lot of mathematicians in the past like that. And then they were working out their way up to overcome with that. Okay, but that's one big problem. All right, and so now, so I was just I've been only breaking down and pointing out the details about the kind of line integral problem this is, but I didn't really get into how we solve that yet. And technically speaking, at this point, you can solve this problem no matter if it's a closed curve or an open curve or whatever, but you can just follow through the parameterization right here and get an answer. But that's not the point. We want to come up with something that's a lot faster and more efficient, okay? That can solve the problem a lot faster and a lot more efficiently. And that's the idea right here. But once again, back at the end of the day, this problem here on its own picture, it's a line integral on a closed curve. And a little furthermore right here. Now, so ever since we start learning about line integral, then any curve or any path is oriented. And so right here in this simple closed curve, it is positively oriented. So what does that mean by positively oriented? Think about any closed loop now. A closed loop, a closed path, it doesn't have to be nice round circle. It could be just anything weird looking, but the point is when it loops around and comes back to the same point, then positively oriented. Okay? Positively oriented means we go around in the counterclockwise orientation. We are going around, okay, but in the counterclockwise orientation. That's another way of seeing it. Or think about if you're moving, think about if you're that person moving on around. I've learned this from some textbook authors right here, but think about if you're moving along the path right here. The positive orientation means if you're moving along the curve, the insider, okay, the inner area of your closed loop is on the left. So the person is here, okay. Then the left hand side belongs to the inner area, and the right hand side belongs to the outer area of that loop. Then that means you are going on the positive orientation. Okay, that's one way. How about another way of explaining it? Of explaining what it means by a positively oriented closed curve, simple closed curve. All right. And so that's one more further detail on this kind of curve right here. And so back on this one, optionally, and I'm only saying optionally, big time, most of the time you only see just a circle right here. Okay, but then by default, we're looking at the positively oriented the closed curve. And so sometimes you may see textbook authors use the circle symbol with an arrow indicating the positive direction. Okay, but that's just optional over here. But most of the time when we see a circle, we can just assume that it's most of the time assume that it's going positively oriented, unless there's some special indication or some special instruction somewhere in the problem indicating it's a negative orientation curve right here. So clearly, with the parameterization currently given for this problem, it's positively oriented. All right, so that's another thing to break down. So now back on this board, let's really put all of those details together into a list so that we can recognize a few characteristics. And so I've been going through a few characteristics of that. But so for this problem, what we realized here is that the curve is a simple closed curve, all right, where meaning starting point and ending point meets together, all right. And then the curve itself, another characteristic number 2 about this kind of problem is the curve itself, right? Curve C, right, is oriented in the positive direction. Right? Those are the 2 major characteristics about this line integral here, specifically about the path. And so, and the parameterization we have here is just one among the many parameterizations. The important point is the curve itself is a closed curve, okay, and being oriented in a positive direction. All right. And so now, in that way right here, let's even recognize a little further. So this is just these are the 2 characteristics on the path itself. But now, if you're looking a little more closely into the vector field itself, and again, of course, everything we're doing here is about a 2D vector field. And so needless to say, it's a 2D vector field right here. But let's look a little closer into this vector field right here. Okay? And so I recognize, so for now I'm just pointing out and bring it to your attention that I recognize that this vector field right here is indeed some gradient field right here. It's a gradient field for the potential for a function, for this function as following: f of x comma y equals x squared plus y squared. All right. And so I'm just pointing it out and bringing that to your attention right here. Anyone viewing this video lesson can quickly verify that this is the potential function of that, or this vector field is the gradient field right out of that potential function. Okay, and so you have enough experience and mathematical experience to verify this. And so my point now is that on top of being, this entire line integral problem here, on top of being a line integral along a simple closed curve, and the curve itself is being oriented in the positive direction, the vector field here, one thing we notice, the vector field, right, is a conservative field. So that's what's going on in this problem. The vector field here is a conservative field. All right. And so in that way, so now let's really get the problem done right here. We track down, we pinpoint these 3 characteristics of the field right here. The whole point is I'm trying to bypass calculating this line integral using parameterization. I just want to use some known understanding, some known the fact that we have learned to solve the problem more efficiently than just going through the parameterization and calculating that as a real integral over over the line with the parameterization given right here. Okay, and so for now, this is one big factor for our problem right here. The vector field we have currently in this problem is a conservative vector field. Okay. All right, and so now we really are ready for solving that problem right here. So because the vector field is realized to be a conservative vector field, and meaning it is the gradient field of some function, and we already knew that the function, the potential function there was the x squared plus y squared. Okay, so we knew this. So that's why at this point right here, we can officially use the fundamental theorem of line integrals to evaluate this. And so the integral here, yes, at this point we have realized that it's an integral for a loop around problem, like that, for a simple closed curve. But then in the end, it's a line integral. So fundamental theorem of line integral says this integral can be easily calculated as the difference between the potential function value at the starting point and the potential function value at the starting point and the ending point right here. We take that difference. So I have to note again from our understanding about the fundamental theorem of line integrals, and this R of A, the vector value function at A is to be a little more precise. The potential value function at the vector R at R of 2 pi. And I see this as the ending point of our path. And we're going to subtract the potential function value at R at 0. And these are, note that these are all the same points. Okay? And so this is the ending point. I mean the starting point. The starting point. Okay? And that's what's guaranteed by the fundamental theorem of line integrals. But then so being a closed curve, ending point and starting point is the same point. So R, think about it, R of 2 pi, according to our parameterization, R of t as a reminder, cosine of t, comma, sine of t. So for this parameterization, R of 2 pi equals that point 0, comma 0. And R, the starting point, R at 0 equals the same point as well. And that's why it's a closed curve. It's a simple closed curve. All right. And so now I'm going to substitute these 2 points into our potential function and calculate that difference. And so in the next step, I'm looking at f of 0, 0 minus f of 0, 0. And our answer comes out easily 0. Okay? And so now, as we were as far as this point right here, we got to the answer to this line integral problem where the integral was along a simple closed curve. Okay? But now as we were going along with this one, constantly remind yourself that, well, it's a closed curve in positive orientation, but keep reminding yourself that f is a conservative field. And f being a conservative field is what allowed us to use the fundamental theorem of line integrals to calculate this line integral completely independently from the path parameterizations. Or in other words, as a reminder, anytime your field is a conservative field, it's path independent. Okay, your field is path independent. That means, so right here in my calculations, okay, the calculation can go completely independent from the path. I only need the 2 points, starting point and ending point. And so as we go along this way right here, we actually think of a even better generalization right here. We solve the problem here for this specific case where we think about a better generalization. So anytime F is a conservative field, and of course it's path independent, okay, so it's leading to F is path independent. And so being path independent, it leads to fundamentally now doing any kind of problem like this, a line integral but along a simple closed curve, okay? Then the answer will really always going to come out 0. Now this problem, the answer came out 0 not only because substituting 0, 0 into the function gives 0 and minus another 0. It's not simply that. Now even if I give out another function, another vector field where it was known to be a conservative field, then consequently it's going to be path independent, and so calculating the line integral along any closed curve, the answer is going to be 0. So why is that? Because just the nature of any closed curve. We start the curve here, we go around no matter how big, how far we go, but we're ending up with the exact same point. And so at that same point right here, starting point and ending point is exact same spot. And so all we do is we take the function value at that start point, I mean at that end point, right? Subtract the function, the potential function at that start point right there. And then we come up with the whole value. So, and it should be, because it's a function evaluated at the exact same point, it's always going to turn out to be 0. Okay? And so that's what's general about the line integral value along a simple closed curve. But now again, I have to remind you, this is only a consequence right out from our vector field being a conservative vector field right here. So this understanding about our vector field is important. Having a vector field being a conservative field right there, it will always lead to the line integral along any closed curve will always turn out 0. Okay? All right. But now, back to this problem. The problem I introduced here was not only intended to be for a vector field being conservative. So I started out bringing in a problem like this, line integral along a closed curve, positively oriented. But then right now the problem here specifically working with a vector field being a conservative field. And so we went through the fundamental theorem of line integrals just fine, right? And then we came up with the answer 0. So it's going to be always 0, 0, 0 anytime your vector field is a conservative field. But then in the end, the problem itself is still more than just that. Because what if, I'm bringing up the question, what if the vector field itself is not a conservative field? Okay, so let me quickly modify. So think about this. What if the problem in the beginning, right? What if the problem in the beginning was and for this purpose right here, allow me to write this in red ink, y comma 2x. All right. Now I want anyone viewing this lesson, let's spend a minute or so, quickly verify for me that this vector field is not conservative. All right. So hopefully you have spent some time, including pause the video if you need to, right? But you have verified that. So the vector field now, I'm putting up this what if here. So what if the problem was given the same exact problem, closed curve, positively oriented, but the field itself was not conservative. Right? So what if we had that field and the field here is verified that it's not conservative? All right. What if it's like that? Okay. And so at this point, think about that list of characteristics of the line integrals here. earlier I pointed out this kind of problem was on a curve, a path C right here. Okay, on a path C being a simple closed curve. Okay, and the path C is positively oriented. Before I made the modification, we further realized, and that was shockingly the most important, the key factor in the problem we've done earlier to get the answer so fast and efficiently. The vector field is a conservative field. All right. So that was the list of 3 important characteristics I've listed down when we were solving that earlier problem. But now, again, I've talked about what if the vector field itself right here, yes, all that, it's a nice simple closed curve going positively oriented. Okay, but what if the vector field is not conservative? Okay, so think about as a larger generality out there, as a bigger generality out there. What if we are conducting a line integral problem, calculating line integral value problem, where the field is not given, right? The field is not known to be conservative. Okay, or let's say f is not conservative, or just generally we're not given that information where f is conservative. And then more specifically, I want to head you into that case where f is not conservative. How do we handle a problem like that? Okay, so I hope you can realize at this point the similarity between the problem here. It's all about a problem where we are having a line integral of a vector field on 2D space, okay, along a path. But the path itself is a simple closed curve and positively oriented. That's the major the feature of the problem right here. But now when it's not conservative, how do we handle that? Okay, now you got to take one advice from me, and it's just the way it is. Surely the fundamental theorem of a line integral does not apply. Does not apply. We can't apply the fundamental theorem of line integrals into this problem because we no longer know, we no longer have that feature where f being conservative, because the fundamental theorem of line integrals only apply to those vector fields being a conservative field. Okay, and that's what we're losing right here. That's one feature that we're losing. So that method I've done in the previous problem is completely irrelevant here. Okay, it cannot be used here at all. All right, so for anyone viewing the video lesson here, at this point when I mentioned about this closed curve, you can still proceed with this problem right here. So our vector field here is y comma 2x, and it's a line integral of the vector field, okay, along a closed curve where the curve C is parameterized by r of t equals cosine of t, comma sine of t, and then t changing from 0 to 2 pi. Okay, so I wrote this integral here so that I'm pointing out for you that anyone viewing this lesson always has a choice to calculate this integral using the traditional parameterization. So we got a provided parameterization. We can just quickly go, that's become an integral from 0 to 2 pi, because that's the interval for our t changing in between. So from 0 to 2 pi, and then this integral here, you've learned that from our video lessons about how to calculate line integral. Then you can turn that into, okay, so y here substituted with sine of t. So we have sine of t, okay, and then And then 2x here, x is substituted by cosine of t, so we have a 2 cosine of t. Okay, and we take the dot product with the dr here from our previous learning. We can turn that into a vector. That's going to be the derivative of r right here multiplied with the dt. That's what dr is. So the derivative of r right here means we have minus sine of t, comma cosine of t. And so now simply take the dot product here, and at this point our integral turns completely into an integral in terms of t. And then so you can always proceed with this problem as an integral from 0 to 2 pi. Okay, and that would be minus sine square of t plus 2 cosine square of t, and then dt. And then yes, you can spend your time calculating this. Okay, and of course, the answer after you spend time doing this right here, it's always good to do some work, and then at the end we have some other backup methods to verify our results later on. So yes, the answer will equal to pi. But I'm not talking about going through this method. So you are more than welcome to try this method. That's why I only set it up, and I pointed out the way to set it up. And this is what I mean the whole time by saying we're going through calculating this line integral using the traditional parameterization method. We stick with the parameterization and we turn that into an integral in terms of t. Okay, and that yes, the answer after you work through your integral here will turn out to be a pi. Okay, but now that's not the method I'm intending for. Okay, so the method that we're about to use here, completely aside from this, and keep in mind, the fundamental theorem of line integrals does not work for this case here, simply because our field here is not a conservative field. Clearly, we have verified that. Okay, and so now the secrets to this problem right here. I can get to that answer. Being pi. I can get to that answer being pi, but simply by using a completely brand new method. And that method here is introduced by, what's so-called the Green's, is introduced in the Green's theorem. Okay, so the Green's theorem is a method that allows you to calculate the line integral on a simple closed curve, positively oriented, right, with a non-conservative vector field, like that. All right, so in that way, let's look at what the Green's theorem is all about. All right, so on my computer screen right here, let's have a look at the Green's theorem. So this is the precise worded definition, the precise worded version of the Green's theorem. So we can look at let D be an open, simply connected region with a boundary curve, C. That is a piecewise smooth, simple closed curve, oriented counterclockwise. So this is the information right here. It's a simple curve, simple closed curve, and that's what the C is. And C is being the boundary of this domain D right here. So before we get too far, let me swing back on the board. Think about the idea now is that anytime you have a closed curve, okay, doesn't matter where your starting point and ending point is, because it's all going to be one point. But being a closed curve, then the insider is a region. The part that's enclosed inside your curve right here has to be a region. And the region here is what it's called the domain D in the Green's theorem worded version. Okay, and so now, and piecewise smooth, it could be, the version I'm drawing right here is a nice smooth loop going around, but it could be something like this. Okay, this is still simple closed curve, but piecewise smooth, meaning one piece is going smooth, another piece is going smooth, but there's still some corners, some straight turn, some sharp turn somewhere. Okay, but in the end, this is still under the same category, being a simple closed curve, and there's a region, there's a domain inside of that. Okay, so the curve C is the boundary here, and the curve C is the boundary here. So at the least, the curve has to be piecewise smooth. That's what it means right there. Okay, and so now let's continue breaking it down further. And so now back to the theorem. See, so let the vector field F be a vector field in two-dimensional space here, be a vector field with components, functions that have continuous partial derivatives and all that. Okay, on D, we'll get to that. And actually, this information right here, you will learn as you keep working with the information. But now the main important part right here, it holds that the line integral for this nice closed, simple closed curve right here. See, that's why there's this circular symbol form. And this is just, now when I gave that video lecture about the line integral, then I see this is another way of writing it. This is another way of writing our line integral, a different expression right here. And so the real important part is here. The line integral along this simple closed curve turns out to be the double integral over the region inside the curve. The double integral over the region inside the curve on the function that's created by qx minus py. You see, that's why there was this form right here to make clear what px and qy is. I mean, to make clear what p and q is. P is the first component of your vector field, and q is the second component of your vector field. And so here we do qx minus py and generate that and come up with that as a new function. So now we're calculating this, and we're calculating this line integral as a double integral on this function over the region D. The region D is inside of your closed curve. All right. And so really, what's highlighted? So the region D is in here. Okay, and the closed curve is here on the boundary. The closed curve, the region D is in here. Okay, and so really what's highlighted is that I have emphasized that when we were on the computer screen, but let me highlight that again. The most highlighted information is, you see, our line integral for a positively oriented simple closed curve can be found by simply we create a function py minus qx. Qx minus py. So that is surely a function of two variables. And then we're going to integrate as a double integral over the regions trapped inside of that domain, trapped inside of that curve. And then we're working with that as a double integral over that region. And that's the main core idea, the most highlighted idea in Green's theorem. All right. And so now, let's see if we are able to use that Green's theorem. Let's see how we can use the Green's theorem into solving this problem right here. Okay, and so along with that way, as a matter of fact, now I no longer call this a problem. I'm gonna now call that the first example. This is our first example, so that we can see how we use the Green's theorem. But the Green's theorem is going to be applied on this line integral where we have that function. So let me spend a minute to reword the problem here. All right, so this is our example 1 right here. This is exactly that problem I brought up where the vector field is not a conservative field. And we've done this throughout our scratch work earlier when I brought it up simply as an introduction problem. And I switched the situation. And then further, we have a path given by this parameterization, cosine of t comma sine of t, and t changing from 0 to 2 pi. So clearly with this parameterization, we realize that this line integral is an integral along a path being a simple closed curve, positively oriented. Okay, and that's the idea. And so with the key factor here is that the vector field itself is a non-conservative vector field specifically. All right. So in that way right here, you got to realize with this specific picture, this simple closed curve right here is a circle, radius 1, right at the origins. It starts at 0 and it ends at 0, 0. It starts at 0 on the x-axis. That's what I meant, and it ends at 0 on the x-axis. Okay, and then so the curve is understood as the boundary. Okay, and then the region inside here. Okay, the region inside, that's the region D being stated in the Green's theorem. Okay, so in that way we have a couple of developments right here. So D right here, right? D is indeed all x and y pair, right? all x and y pairs of values satisfying, see, x squared plus y squared in rectangular coordinates. X squared plus y squared being less than or equals 1. And that's what it needs right there, okay, in rectangular coordinates description. That's how I'm seeing it. That's the region D. And now since we starting to get into this kind of problem where we always have to differentiate, to make clear distinction between where it is to be a boundary and where it is to be the inside, the interior of a region, okay, of a closed bounded region. So allow me to show this symbol right here. Let's say you have a region enclosed by a closed loop. So you got a closed loop, a simple closed curve right here. So the boundary, so the region inside, you can call it D or you can name it whatever. But then the boundary, we use this notation. The boundary, that partial derivative symbol, but we attach that together with the name of the area of the region. That's indicating the boundary. So this is the boundary. This symbol means the boundary of the region D. Okay, so D is the interior, or D is the whole picture itself, but this symbol right here, okay, is the boundary, what's going around right there. Okay, that's just one notation I would like to point out so that in case you will see that here and there in different textbooks, you won't get shocked. All right. But so for now, with this problem right here, let's get to it using the Green's theorem. The integral at first is the integral along a closed, simple closed path, where the x component, the first component is a function y, dx plus, so this is p right here, and the other component is a 2x. Okay, so this is in one way of notating our line integral along any path like that. Okay, but what you need to realize is this is p and this is q. They're all functions of x and y. And so in that way, I am going to calculate, I'm going to quickly calculate, how about py? Okay, the partial derivative of p, but in terms of y. Okay, that's one thing to remember. And so with that, we're looking at 1. I'm further going to calculate qx, the partial derivative of this function q, but in terms of x. Okay, and that's one thing to remember. And then that here gives me 2. Okay, and so putting it all together, this line integral, according to Green's theorem, can be calculated as a double integral over the region D. So the region D, I made that indication in a picture on the other board already. Okay, and then here is our function qx minus py. So qx is 2 minus py is 1. And so this is now a function of two variables. We're glad that it turns out to be, at this point, a constant. But it could be other function in other cases. Okay, but qx minus py. And then integrating this as a double integral over that region D. So this is just now our standard double integral problem right there. All right, and so in this way right here, we have so many different ways to approach this problem. Anyone can go directly seeing this as a rectangular coordinates, right? And then do the double integrals over that region. And then furthermore, with a double integral like this, you also have your choice of integrating it using integrating this double integral using polar coordinates, and you have all of those options at this point right here in your learning. But then most precisely speaking, I can just simply see this as, see, 2 minus 1 is really a double integral dA. I mean, it's just for this problem, as how we further work into this problem, then it's just going to be simply the area of D, just for this problem, because it's 1. 2 minus 1 is 1. So the double integral over that region, right, of the function 1 times dA right there, that's simply just going to come out with being the area of D on this problem. And so now that comes out with your circle, center at 0 with radius 1. So the area of this region, the area of this circle has to be pi. All right. And so this answer here simply agrees with the answer we have already had using the traditional parameterization method. Okay. And so ladies and gentlemen, this is how we apply the Green's theorem, okay? And as a tool to effectively calculate the line integral along a simple closed curve, where when your vector field is not a conservative field. All right, and that's how it's done. All right, so what else is so useful about this Green's theorem? Okay, what else is so useful about this Green's theorem? Think about, you see, it was done very quickly because, again, I have shown that problem earlier. The same line integral along this simple closed curve when it was, okay, and then our vector field was y, comma 2x. See, the time we spent doing this using the integral, we're going to end up with this integral. Okay, that was 2 cosine square of t minus sine square of t dt. And it took quite a few steps to arrive here, and then it's going to be even more challenging to get this answer into a pi. It takes some more. I'm not saying that it's impossible to get that. I'm not saying that, but it took a lot more steps to get into a pi, and it already took some good number of steps to get here. That's the usefulness of the Green's theorem. The first thing, Green's theorem took us just a few lines here, thanks to the Green's theorem. Okay, so that's one usefulness of the problem, and we arrived exactly at the same answer. Okay, and so as another usefulness of the Green's theorem is that, you see, without the Green's theorem, before Green's theorem came out right here, I guess if we are doing a line integral on a simple closed curve, this is the only method before Green's theorem was born, before Green's theorem came out. And so think about this. This is one of the worry. I was under that worry as well when I was doing that. You see, what if our closed curve here has starting point and ending point right on the x-axis, right? So for anyone who did not know anything about the Green's theorem, there is this worry that deserves your attention. There's this worry. Does it matter? Will it change the answer if the starting point and ending point being here, or the starting point and ending point being here, or starting point and ending point being here? The major problem is our curve here is being a closed curve. So any point on that closed curve could be a start and being the end. And so think about it. For example, the curve could be from pi over 4, okay, to 9 pi over 4. That's a completely different starting end point. Starting point and ending point. It starts here, it's ending there as a closed curve. Will that change the final answer? You see, and to verify whether it changes the answer or it won't change the answer, we got to go through a few different starting points, and it's still hopeless that have we reached enough generality. And so, thanks to the Green's theorem, with the Green's theorem right here, we are completely independent with where that starting point and ending point is. The Green's theorem say, hey, really the answer is just obtained by this works right here. And so all we have to worry about is set up that qx minus py, okay, and then work it out as a double integral. And so starting point and ending point is completely disregarded. Okay, that piece of information is completely disregarded. So that's one big usefulness about the Green's theorem here. And again, the limitation for the Green's theorem is it's only for those line integrals where your curve here is on a 2D path here, and your vector field is a 2D vector field. Okay, so this path here has to be a path on the x and y plane. Okay, and that's the one limitation of that. So C is only on the x and y plane. All right, that's the idea. And as a more general, as a better generality, C is only on one of the three planes right there, of the three floors right there, either the x and y plane or the xz plane, if we express the vector field differently. Okay, but then allow me to point out that usefulness in another example. So here we go. Let's look at example 2. All right, so this is our example 2 right here. And as we will get into it, you will understand a better usefulness of the Green's theorem. Okay, so now to get started into this, let's think about this region right here. Let's think about the curve itself. And clearly the problem is indicating it. So now we have a line integral, right? So you can see that the dx component right here, this is the p component, the p of x comma y component of your vector field. And then this is your q of x comma y of your vector field right here. So clearly your vector field is a two-dimensional vector field. The path here, it's indicated here with the symbol. It's going to be a line integral along a simple closed curve. But what is that curve? What is that closed curve? It's a closed curve that's connecting. It's being a path connecting from, so it's connecting, starting at that point right here. It connects over to 4, 1. So 1, 1 connects to 4, 1, connects to 4, 5, and connects to 1, 5. So let's have a picture of those. So I don't need any advanced computer software to get this. Okay, 1, 1 is about here. All right, and then 4, 1 is about there. So we're connecting that in that positive direction. That means, and maybe for now I'm a little too rushed about that, but let's not worry about the orientation yet. But see, we start here and we connect to 4, 1, and 4, 1 we connect to, okay, 4, 5. So I'm about up here. Okay, so 4, 5 is here. So I'm connecting that way, right? And then 4, 5, and now back to, and then 1, 5 is over here. So from 4, 5 we connect over to 1, 5. Okay, and then from there, of course, we can connect to back down to that beginning point like that. So it's a closed loop. So we got these 4 vertices right here, and it creates for us a rectangular shape. Okay, it's a rectangular shape. And then, so that's the idea right here. And this is the picture where I so-called it's only piecewise smooth. Okay, and so in the positive direction means it goes from start here, it goes that way, and then it goes this way, and then it goes this way, and then it further connects back to that starting point right there. Okay, but then and for this problem, let's quickly take a look at the vector field. The vector field is x squared y comma y minus 3. Okay. We now have the tool to quickly verify that this vector field here is not conservative. We can do the py check with qx. Okay. We can quickly do that check, and it's easy to verify that py is not equal to qx. We can easily check that. Okay. Simply because, see, py is right here, right? So py gives simply because py equals x squared and qx equals 0. And that's why I pointed out that result earlier. Py is not equal to qx. And so in this case, clearly our vector field here is not conservative. And this is where the usefulness of Green's theorem comes in right here. Okay, but then the better usefulness of Green's theorem is that it's right here. We don't have a nice closed loop. So think about if we don't want to use Green's theorem, without Green's theorem, this is what we have to do. We break that into, we have to really, this whole path, we have to see that as, allow me to switch to the other board. Okay, so now back to what I was saying earlier, without the Green's theorem, the path we currently have going in positive direction, but we have to see that as 4 separate curves. This one curve at the bottom right here is called C1. This curve pointing up right here is called a C2. This curve pointing over is called a C3. And this curve pointing down right here is called C4. And so the entire line integral right here along that closed curve, okay, must be broken up. I'm talking about if we were attempting without the Green's theorem. This line integral of our problem must be broken up into the 4 separate little line integrals. One of them is on, but now each one of these is no longer a closed path. So I don't have that circle symbol over here, but it's a line integral on C1 from here to here. Okay. And add that to the result of the line integral, same vector field, but as a line integral on C2 from here up. Okay, and a line integral for the same vector field, okay, on C3 from this point over, and the last result right here from C4, okay, along C4, and none of these now is a line integral on the closed loop. So this is what we need to do. What we needed to do if we were doing it without Green's theorem. That's the plan right there. Okay, and so it's gonna. I mean, expectedly, it's going to produce a lot of work if we would be attempting that without the Green's theorem. Okay, but now thankfully with the Green's theorem, we don't need to do any of this. Okay, we don't need to do any of that. So again, with our line integral along this simple closed curve, and we got x squared y dx plus y minus 3 dy. This can simply be done by finding the double integral, okay, of first of all, px qy we have found previously. I mean py qx we have found previously. Qx is 0, py is x squared. Okay, so 0 for qx minus x squared for py. We're going to treat this as a sum function in terms of x and y. We're going to integrate this as a double integral over the region D. So D is our rectangular area right there. So that's the region D right there as a double integral. Okay, so now with this problem, it's going to turn out very simple. Okay, this region D right here will now have the following description in rectangular coordinates. It's x changing anywhere from 1 to 4. Okay, and y is changing value anywhere from 1 to 5. Okay. And so with this integral, now we can successfully turn that into an iterated integral, okay, in whichever order that we would prefer. So I will go with the x inside. Okay. So I'll go from 1 to 4, right, and minus x squared dx, and then I'll do that again from 1 to 5 in respect to y. Okay, and so at this point we can easily spend our time working through this iterated integral. And so the answer should easily come out. So allow me to skip the steps right here, because anyone viewing this video lesson is experienced enough with doing line integrals right here. And so the answer will finally come out being minus 84. Okay, it's being our value. All right, so that's how easy it is. So instead of going the lengthy work by breaking it up into 4 separate line integrals along 4 paths right here, it's just all in one package using the Green's theorem. We got it done in a couple of steps. And of course, I hid away a few steps here, but that's not important because I believe anyone viewing this lesson is experienced enough to do this very easy double integral over a rectangular region, a very rectangular region right here. And so the answer can come out easily being minus 84. I'm running out of board space, so I didn't even bother getting into the actual steps of this little integral work right here. All right, so that's the idea right there. Okay, and so at this point, after seeing about 2 examples, the earlier example and this example now right here, I'm still leaving this problem right here so that you can see. Now, if you're reading closely with any of your textbook that you are using for your class right here, then this version of the Green's theorem we are using, the version we're seeing for the Green's theorem. This version right here of the Green's theorem is quite often referred to, and actually it is the one, but some textbooks skip that name, but many other textbooks refer to that as it's a Green's theorem, but of the circular form of the Green's theorem. Okay, so this Green's theorem version that we're learning is called the Green's theorem. It's a Green's theorem, but then comma circular form. Okay, so what does that mean by it's a Green's theorem, but comma circular form, or some textbooks authors put parentheses there. Some textbook authors say the circular form of the Green's theorem. Okay, there are so many ways of putting that, but in the end, there's something about circular form like that. So what exactly does that mean? It's because the Green's theorem, the version of the Green's theorem that we are currently studying here, helps us solve those problems where we're looking at a closed path and we're going along the path. We're going along the paths. Okay, we're going along the paths. So that's why it's called circular, because we really are following along the path. We're traversing along the path. Right there. Okay, but so for you to be aware, of course, it's not being delivered right here in this lesson yet. Okay, in some other lesson, I will go over that kind of material. But there are also the Green's theorem version. I mean the Green's theorem, but for they call that the flux form. But this is to be covered in a different video lesson right there. So what's the idea of a Green's theorem for a flux form? In order to understand what the Green's theorem for the flux forms right here, you have to understand that line integrals we have learned so far is only the kind of line integral where whatever path that is doesn't have to be closed path or what, but we are in the end going along the path. Okay, that's the kind of line integral we'll focus to so far. And then of course in a different video lesson I will cover the other kind of line integral, but there are right here, let me briefly mention it, there are line integrals out there where there's a line in your vector field. There's a line in your vector field, and we want to study the line integrals where we want to measure how vector is going through, instead of going parallel, we're going we're crossing through the path right there, and that's called the flux integral. So at each point right here, there's a vector on the vector field that's normal to the path right here, and then we're accumulating all of those the products right there from beginning to the end. We come up with a line integral, another version, another form of a line integral we call the flux integral. Okay, we call that a flux, and so there's a Green's theorem that's applied to the case where you got a closed loop and then your vectors are pointing out or going across. Instead of going along, it's going across the loop like that. Okay, and we're accumulating all of that. So calculating that kind of line integrals, we have to use what's so-called the Green's theorem, the flux form. But of course, it's not going to be covered in this particular video lesson like that. All right.